Pretty much.
So it should look like this. Sorry, yeah. I was backwards and not off to a good start. So that would be, we'll just make it 0, 9, 6, and then we'll have, what's the next one?
1, 1. I was about to say
1, 1, 0, and then 1, 2.
I forgot 8. 2 8s.
I forgot the 8.
Oh no, like on the 1 1. It should be 0 8.
0, 8.
And then 1 2.
1, 2. Sorry guys. And then we'll need to have a sheet that says that 1, 4, and you have to say what it means.
I don't know why there's so much
Alright, so if we have some data that is skewed, well, that's not very, that's not looking very skewed. There we go, that's better. Our median would be a more accurate measure of center, and what's going to happen is the mean is getting pushed out that way. So, mean is less than the median. No, definitely not. The mean is great. Okay. Small company is estimating its photocopying expenses. Finds the mean number of copies made per day for the past 12 months is 258 copies, with a standard deviation of 24 copies, which is the following is the correct interpretation of the standard deviation. Not this one. 95% of the time, no. The difference between the mean number of copies and on average, love it. Because our definition of standard deviation, right, is that it is the average amount that each data point is from the mean, or on average, how far away each data point. All right. High school teachers asking classes to fill out a survey, ask their age, gender, the number of years they lived, and their current address, their favorite school, subject, and whether they plan to go to college or school. Which of the following best describes the variables that are being Alright. So we got to figure out which ones are quantitative and which ones are categorical. So here we go. Let's just go ahead and quantitative number of years, quantitative school subjects.
Is age quantitative or
Age? It is definitely a number that I could divide and find a mean of and all that. So we got two quantitative, so I'm looking at either this one or this one, so how many categorical are there?
So there's
1, 2, 3.
Yeah, so it's
Weren't there 3 categorical? There are 1,
but ages
2.
number of years is
1, 2, 3. 3 categorical, 2 quantitative.
okay, 2 quantitative.
Yeah.
Oh, I see. Okay, I thought those were 3 and 3.
All right. Types of American men aged 18 to 24. Actually, I'm going to go ahead and take this one. Oh.
Are you recording?
That's not what I want to do. That's not what I want to do either. And so, we'll just select this. Oh, I'll just have to go 68.2.5. Let's figure out where 5% is. All right. So the idea behind this problem is that right in here in this interval we have 95% of the data because of our empirical rule, aka the 68. Oh, my bad. I'm in the wrong spot here. The 68, 95, 95% here, right? 99.7, right? So it tells me that right in between here is 68% of the data. In between those two intervals is 95% of the data. And remember, in between these two, we have 99.7% of the data. So what do these intervals represent? This is 1 standard deviation away from the mean. And this is 2 standard deviations. This is 3 standard deviations. So what I'm looking for are the interval that is 2 standard deviations away from the mean. So this is going to be 68. So 68 plus 2.5, 70.5, and then 2 standard deviations. My bad. 70.5 is going over here. A little rushed today. Sorry.
Wait, so what are the 68, 95, 70?
68, 95, 99.7.
95.7?
99.7.
And then, so we're looking for...
We're looking for how far is 2 standard deviations above and below the mean. That's really what the question is asking for. So 2 standard deviations below is at 65. My bad. How about 63?
Yeah.
Really not on the game today. have 2 standard deviations above is going to be add 5 stores. And that's actually not in that spot. So what we're looking at is this interval right here between 63 and 72. That looks like a minus. I'm not going to write that. So between 63 and 72. Let's look at what we got.
73.
Did I just not add correctly?
Yeah. Because you're at 70.5 plus 25.
Yeah, I'm doing really well today. It's 63 and 73?
Yeah.
Alright, wow.
You just need to remember the 60.
Yeah, I just can't add. Thanks. Okay. Well, what percentage of men are over 70.5 inches tall? So we'll go back to that. Oops. 70.5, so we're looking for an x value of, So we could do this a couple different ways. We could use this empirical rule and do some subtraction and stuff like that, right? Or we could, I think the quickest way to do it would be to just find out. If you're on a multiple choice, you don't have to do a lot of extra work. All you got to do is go to your calculator and go normal CDF. And we're going to go lower. It said above 70.5, right?
Yes.
Lower.
Why is it?
Upper. Mean. Standard deviation. I think that's the quickest way to get that. So we'll go ahead and do that real quick. So if I'm doing this test, I don't have to write down this normal CDF. I'm just going to get out my calculator. I'm going to hit my calculator key. I'm going to hit menu. Probability. Distributions. I'm going to go normal CDF.
Why is CDF not?
It's cumulative, so it's finding an area on an interval. So we're going 70.5, upper bound 10 to the 99th. Mean was 68. 68, thank you. 2.5. Okay. Approximately, well, what do we else? Approximately 16.
So how would that work out with the
You want to use the empirical rule and break your brain? No, you're not going to break your brain. It's just you have to think a lot more. So what you're looking for then is this shaded region if you're going to use your empirical rule. So if that's 95%, right? Then yeah, that's 2.5%.
Yeah, so I'm confused.
Why is that not working? Hold on. It's saying are above that value.
That's why I was confused.
Huh. 70.5 was 2 standard deviations away, right?
70.5.
No, 70.5 is one standard
Yeah.
deviation.
Oh yeah.
That's why.
And it's asking for.
So then both the shaded areas that I have right here then represent 32. What? Okay, these two shaded areas, right? If right, so we're talking about this interval right here, 68, right? Which means that those two shaded areas are 32%, right?
Oh, got it.
If you take that one away,
Yeah.
then what you got left is 16%.
Yeah, I thought it was 250. Thank you.
Hey, which of the following properties is true for normal density curves? They are symmetric. Indeed, they are. The curve reaches its peak at the mean. Indeed, that is true. 95% of the area under the curve is within one standard deviation of the mean. Incorrect. So the answer is C. Thank you. Kitchen appliances don't last forever.
I was just talking to Mr. Fresco about this earlier.
Huh?
I was just talking to Mr. Fresco about that earlier.
That they don't last forever?
Yeah. And they're like pretty much built so they don't last forever. Oh, weird.
I got a coffee grinder from Starbucks before my wife and I were married. When we were living in sin. We were just living together in Phoenix. And I still have it. I still use it like every morning. It's amazing. We have been together for 18 years. So, pretty unreal. Mean is 9. Standard deviation of 2.5. So, it's definitely exceeded. I would imagine the probability that that would occur is probably fairly low. This is a Starbucks grinder. Starbucks brand grinder is amazing.
So could I do normal?
Yeah, so I would just do, so, like, if we were on a free response, I would have a bunch of work to do, right? I would have to show z-score, I would have to show the shaded region that I am calculating using, and then I would have to write, you know, the probability that, or what percentage, so I would have to, you know, write what that area is and stuff. We're on multiple choice. I need to go as quick as possible. I need to be efficient. There are a lot of multiple choice questions, and they're hard. Some of them will take you a long time to answer. So the ones that don't take a long time, get out your calculator. We're looking for 10 years. I can even just go up here. Does it say more than 10 years?
Yeah.
So I can even, I almost have this exact thing in here. I can copy it. I'm going from 10 to infinity-ish. And my mean is 9.
And
Oh.
2.5, yeah.
And 2.5? So, I mean, boom, already done. Quickity quick. So approximately 34.5. Where are we at there? Ooh, that's a B.
Wow, I think that's still something I do PDF.
You don't know the difference between PDF. PDF is finding a location on the distribution for you, and CDF is finding an area on the distribution. If you do PDF, it's going to tell you what the location is, like the relative location. It's just going to tell you how many standard deviations away from the mean it is. You're going to get an area under the curve for CDF. Yeah, it's weird. Here we go. Oh. It's like a ranting going mad, man. Here we go. All things being equal, larger automobile engines consume more fuel. You're planning experiments to study the effect of engine size in liters on the gas mileage in miles per gallon of sport utility vehicles. In this study, what would you do? You want to know, does engine size affect gas mileage? In other words, can you predict gas mileage based on engine size? That'd be another way to put it, right? In which case you would put engine size here, and you would put gas there, right? What do you think is going to happen? Do you think what's going to happen to your gas mileage when your engine, like your four-cylinder, your friend's four-cylinder car fills up for about $30, goes like 2 weeks, right? Your friend's Jeep or their Expedition or whatever, right? Their big SUV, right? It's got like 6, 8 cylinders, and they spend $60 to fill it up, and it lasts a week.
Yeah, $70.
Yeah.
It lasts maybe 6 months.
So what are you gonna think? You're gonna think that there's gonna be a negative association, right? So engine is the okay. Gas mileage is response. Oh, that's it. That's all it says. Gas mileage response, negative association, right?
So the y-axis is response variable, x is
Absolutely. Yep. Remember, your x-axis is your explanatory variable. Your y-axis is your response variable. If as your x increases, your y decreases, we're going to say that that is a negative association, and the opposite is true. Opposite is true of a positive association. Okay. A set of data describes the relationship between size of annual salary raises and the performance ratings for employees. We've got a least squares regression equation. Y hat equals 1400 plus 2000x, where y is the raise in amount of dollars, and x is the performance rating. Which of the following statements is not necessarily true? So let's talk about the situation first before we get anywhere. So we're trying to see if we can predict the annual salary. Let's see. Why is the raise? Yeah, where we can predict the raise based on the performance rating. So for each 1 point increase in performance rating, the raise will increase on average by 2,000. I'm liking that. I'm just gonna keep that aside and make sure there's not a better answer. The actual relationship is linear. No, we can't say that it's actually linear. We're making an approximation.
Well, we're looking for the one that's
not. We're making a prediction. The predicted relationship between salary raises and rating is linear. We can say that, but we can't say the actual. And what was that?
We're looking for the one that's not true.
Oh, not true? Dang it. Oh. Well, then I like that one. Yeah, thanks for helping me out with that. This is true. I don't think that's true. This is true, right? When x is 0, y is 1400, that's true. Correlation is positive, yes, because the slope is positive. If the average performance rating is 1.2, the average raise is 3,800. 2,000 times 1.2 plus 1,400.
Yes.
Yes. So then that leaves us with.
Why is that not true? So you can say the actual.
So you can't say actual, you can say the predicted, right? We're not allowed to actually say that that's actually what's happening. We are making predictions. Copy machine dealer has data on the number of copy machines at each of the 89 customer locations. Got some summary calculations where this is our mean of our x, we got the standard deviation of our x values, we got our mean of our y values, the standard deviation of our y values, and we have our correlation, or R value. About what percent of the variation in number of service calls is explained by the linear relation between number of service calls and number of machines. And this is essentially, we're being asked, what is the correlation coefficient? Right, so we've been giving the correlation R. It would be very tempting to take this, right? But that just tells us how strong the correlation is between our explanatory variable and our response variable, that R value, right? And that R value always has to be between -1 and +1. With R values closer to 0, signifying that there is a very weak correlation, right? R values closer to 1 and -1 are telling me that there's a strong either positive correlation or negative correlation, respectively. So, what we need to do is square that, right? Because remember, our correlation coefficient is R squared. So we can take 0.6 and square it. And we get approximately 0.74. There it is. Now it looks like 4%. All right, we're going to draw a sample of 5. Ooh, here we go. Let's use that. Let's use our random table of digits. A random sample of 5 without replacement from a population of 50 households. Suppose the households are numbered 01 to 50. So we're not going to do 00 to 49. That would be another option, but we're not. And suppose that the relevant line of the random number table is this. All right, let's select 5 households. We selected household 11, household 32, household 23, 56. It does not count, right? It is outside of our range. 92 we will not select. 96 we will not select. 23 will be selected. 79 not selected. 08 selected. Are we almost there? And 42. So it should say 11. Well, did I do? Yeah, I did. I did. Okay. Oh well. So we're looking for 11, 36, 23. Oops. We can't count that one either, right? Can't count this one. So I did a proper amount.
Which one?
There are 2 23s. We can't do 23 twice, right? So 11, 36, 23, 8, and 42. Some good distractors in there as well. Some good distractor answers. I like them. Very easy to call. You don't understand. Searching for core resources is like going on a treasure hunt sometimes. And sometimes 2 hours later you're like, okay. Hey, maple sugar! Does it have sugar in it? No. Okay. You got it? You really like maple syrup. Okay. Yeah. trunk diameter of sugar maple trees in a large forest. There are too many trees, excuse me, to list them all and take a SRS. It just triggers me right now. I want to say an SRS. So he's going to divide the forest into several hundred 10-meter by 10-meter plots and select 25 plots at random. Measure the diameter of every sugar maple in each one. This is an example of what? Which one is it? Huh? And it is. Is it cluster sample? We never even talked about that. Right? Simple random sample, you just randomly sample things from a large group, right? Stratified sample, we would have to classify them by some characteristic, you know, in the sun, not in the sun, right? Something like that, I don't know. How you can even do that for trees. And a convenient sample, I walked through the forest, the first 20 trees I saw, I measured them, right? That's it. Okay.
So what's a multi-stage?
I don't know. It's just there to throw you off. In no statistics book have I ever seen that definition. It might be a thing, but I've never encountered it.
Not a thing.
It's not a thing that you need to know. Right. So, Mechanicsville, 25 cars. Which of the following is not correct? A random sample case. The sample may not be represented, which is not correct. Samples may not be representative of the cars in Mechanicsville because mainly students park at the Davis High School. That's true. So that's out. If the particular parking space is vacant, we can simply select another parking space at random because it is unlikely that space vacant is related to the color of or manufacturer of car. I know I said parking space. Sorry, there are none of those in here. So. I was in high school too. That's
Oh,
nice. I'm really almost out of time. That's killing me. Alright, well, we're going to hit the pause button. And continue.